We talked about regular languages and we talked about context-free languages. Regular languages can be recognized using finite automata. And context-free languages can be generated using context-free grammars. Now, in today's lecture and in the next few lectures, we will be talking about programming languages or compilers, how context-free grammars are used in compilers to represent programming language constructs, and how this can be used to do the recognition, how we can recognize, how can we check a program if it's syntactically correct or not. Now, here's the interesting idea. The interesting idea is that in compilers, finite automata are used to do scanning or lexing, which is dividing a program into tokens, like x1, 2, 3 equals a11 plus b22, or let's do, instead of b22, let's do 24.5. So in this case, the scanner, which we talked about in previous lectures, is going to divide this string into tokens. And this is going to be based on regular expressions. So there are regular expressions that define the different tokens, or the different parts of speech of a programming language. Like this will be recognized by the scanner as what? As an identifier or as a variable name. So this is an identifier. This will get recognized as the equal sign or the assignment operator. What's interesting here is that this assignment operator, for example, it will have a language. There will be a regular expression for describing a language that consists of a single string, which is this string, that represents the assignment operator. So there is a regular language that consists of a single string, which is this operator. And of course, now the language that represents the set of all valid programs from microsyntax point of view, microsyntax, by microsyntax I mean looking at the lexing or scanning level. So at the scanning level, the language the language of all strings or all valid programs is going to be the union of all of these languages. So there is a language for identifiers, a regular expression for identifiers. There is a language for the assignment operator. This is what? Another identifier. So this also belongs to the same language. This is an operator. So this is a language by itself, a language that has only this string in it. So this is the plus sign, whatever, or the add operator. And this belongs to what? This is a number, or let's say, numbers could be integers or floating point numbers. This is not, this is not the issue at this point. And this is again the end of statement, symbol. So the language of all valid programs. And now you can think of a program, no matter how long that program is, even if it has millions of lines of code, you can think of it as a huge string. And checking the syntax of this program at the scanning level is just checking if this program, if this huge string, which is the program, belongs to that language, that regular language, which is the union of the language for identifiers, the language for this operator, the languages for the different operators, language for numbers, languages for everything, for every token or every part of speech in that programming language. Okay. So now, start thinking of a program as a huge string of characters. Now, this is at the scanning level. This is only for the sake of dividing this program into tokens, but this is not enough, right? You can have a program that has valid tokens but invalid syntax, like something like 24 equals A22. So this consists of 3 valid tokens, but it's syntactically incorrect. So this is a number or an integer. This is an assignment operator. And this is an identifier. Now we need another level of checking to check for the higher level syntax, the actual syntax, not the micro syntax. So this is the micro syntax here. So this is microsyntactically correct. At the micro syntax level, this is a valid token, this is a valid token, this is a valid token. But these tokens together do not make a valid statement in a programming language. So today's lecture is going to be about statements. Now we will be working on a higher level, at the statement level, at the programming language construct level. And for us, in today's lecture, these tokens that are recognized in the scanning phase are the terminals for us. So at the syntactic level, at the statement level in a programming language, this is a terminal, and this is a terminal, and this is another terminal. So the tokens that are recognized by the scanner become the terminals for the grammar that will describe the syntax of the language, the syntax of a valid statement in a language. Okay, so tokens tokens recognized by the scanner become the terminals for the grammars that define a valid syntax. Okay, so they become the terminals, or the, if you will, the symbols of the alphabet. So our alphabet at this level is going to be this. You can call it T, or you can call it sigma. It's going to consist of identifiers, numbers, and then plus, minus, multiply, divide, and you also have the keywords like if, else, and by the way, keywords are going to be trivial to recognize at the scanning level, right? For a keyword like if is a language that has only the string if in it, and that's all. So it's a regular language that consists of a single string, and if is just the only the string in that language. So these are going to be our terminals, or our symbols of the alphabet. So now we will define grammars in which these guys are terminals to define the correct syntax of a language. And so any questions before we write our first grammar for a programming language? Any questions on what has been covered so far? Okay. So our first grammar is going to say, okay, an assignment is an identifier with the equal. Let's say identifier equals identifier plus identifier. So this is a grammar. Of course, this is not general enough. We will generalize it later. But let's look at this. So this is saying that, and in fact, on a higher level, you will have something like a statement is an assignment or other kinds of statements, like conditional statement or loop or others. So let's not worry about this. But a valid statement is going to be an assignment statement or a conditional or a loop or other kinds of statements. The assignment statement consists of an identifier, then the assignment operator, then another identifier added with another identifier. Of course, to make it general, it doesn't have to be add, right? Instead of add, we can say, we can define a variable op identifier, and then our op is plus or minus or multiply or divide. Does this grammar make sense to everyone? Okay, so this grammar defines a statement that consists of an assignment statement in which there is an identifier added to another identifier. Now, if we do, let's do a derivation for, let's say, this. x12 equals a1 plus b2. So the derivation for this let's have our let's have assignment as our start variable. So I'm showing this just to show you where this fits in the bigger picture. But for now, let's not worry about other kinds of statements for the time being. So let's now assume that our assignment, we're only looking into assignment statements. So in this case, our assignment is an identifier equals identifier operator identifier. Now everything here is a terminal except what? Everything at this level is a terminal. So this is a terminal, as we said. This is a terminal that will come from the scanner. This is another terminal. Terminal. Is this a terminal? No, it's not a terminal, but this is defined as one of 4 terminals, and in this case, the op is the add operator. So this is a derivation. Now clearly this is not general enough, right? Why isn't this general enough? Because in general, an expression in an assignment statement does not necessarily consist of one operation. How about this? Minus, let's say, to be consistent, C3. Now, will this grammar generate this statement? No, it will not generate this statement. So this grammar is not general enough to generate this statement. This grammar says you can have only one operation, right? So let's generalize it. So let's say, okay, in general, it's an identifier equals an expression. And then our expression. Now, how do you think we can define an expression in a way that will accept an arbitrary number of operations? How do you think we can define the expression? What do we need to use in order to define an expression such that we have an unlimited number of operations in an expression? So we can't just, we can't say, okay, expression is, say, identifier, op1 identifier, op2 identifier. If we do this, we will have a limited number. So you can say op2, op3, and then you can write as many ops as you can tolerate, or you have time to. But it's obviously it's not the right way to define the expression such that an arbitrary number of operators is accepted. What do you think we need to do? How would we do that? Yes?
Could we put an identifier in the assign and then put op identifier in the expression and then keep on calling the expression?
So what is keep on calling in grammars?
Recursion.
Recursion, yeah. So we need recursion. So the answer is that we need recursion in order to do this. So our expression can be an expression op identifier, and then op is plus or minus or multiply or divide. I was about to put this. I'm just used to writing, to putting this at the end of everything I write. Okay, so it doesn't belong here. Okay, so now, well, is this a good definition? Is this a good grammar? A good production? Or what's wrong with it?
Well, it won't end.
Right. So it's recursion with no base. So we need a base. And the base for this recursion can simply be what? Identifier, right? So you can have, x12 equals a1. And a1. And this is just a valid, the expression, the simplest expression will have only one identifier in it, right? But this will allow us to have as many identifiers as many operations as we want. So let's try to use this now to express this expression to do the derivation for this assignment. So now we have an assignment, and this assignment is an identifier equals an expression, and we have this end of statement. And then our expression is expression op expression, okay, and then one of these expressions is going to have in it, one of the expressions is going to be just a single identifier, and the other expression is going to be expression op identifier. Sorry, we don't have expression op expression. We have expression op identifier. We don't have. Yeah, so we have expression op identifier. So this is the only one that can have another expression op identifier. Is this a complete derivation? No, we don't have terminals yet. So, okay, so what's this op? This is the plus, and this op is the minus. Well, let me. Now, what's this identifier? This is the x12. What's this identifier?
B2.
Yeah, so, well, this is going to be the B2 because the A1 is going to be this. Okay. So by the way, don't skip rules in the derivation. So we don't have a rule that goes from expression to just A1 or A2. So expression can be an identifier, and an identifier in this case is A1. And what's this identifier? C3. Okay. So any questions about this derivation? Does this look like a valid derivation? Yeah. So in fact, this looks like this is a valid derivation for this definition of an assignment and an expression. And clearly we can use this to to represent any expression that consists of identifiers, right? And in fact, we can generalize it. We can further generalize it, and instead of having an identifier, we can have also what? Numbers. Yeah, so we can further generalize it, and we can have also numbers. But there is a problem with this. Now, let's consider this. Now, what will be the derivation tree for this? Now we'll just replace the minus with multiply. Now, is this what we want?
No.
Why not?
Order of operations.
What's that?
Order of operations.
Yeah, the precedence. Yeah. So this doesn't satisfy the precedence that we want. So this is generating this derivation tree. By the way, so this is what we call the derivation tree. Derivation tree or parse tree, which in compilers the parse tree will become what we call the abstract syntax tree. So in this course it's not important to understand the difference between a parse tree and the abstract syntax tree, but essentially they're the same, but the abstract syntax tree has more abstraction. But the idea is in a compiler, this will get processed when code is generated for this. This will get processed by an algorithm that will generate code, and that algorithm is going to traverse this tree in DFS order. And traversing the tree in DFS order would do the add first because it's on a lower level. So it would add A1 and B2, then it will multiply the result by C3. So it wouldn't do what we want it to do. Okay. So do you see the problem with this grammar now? Now I'm gonna modify this grammar in a way that will capture the precedence that we want, the precedence rules that we want. By the way, let's now forget about the assignment too. So let's just concentrate on the expression, and let's see how we can come up with a grammar that will capture the precedence relation. Okay, the idea is the following. Yes?
When we added the number, should there be a semicolon after the number, or does the semicolon go away altogether?
No, in the expression there is no semicolon. The semicolon was on the higher level. It's part of the statement, the assignment, right? So the assignment had the semicolon in it. So for now, forget about. Let's focus on. Let's work at the expression level. Now we know where it fits, right? So we'll just focus on the expression level. We're trying to get the expression right. Okay. So now the idea in math, in order to parse this correctly. So in math, what do we call this? What do we call this? So this expression, this mathematical algebraic expression, consists of, sorry, not this, consists of two, what? Two things. What are these things? What do we call them? In algebra, this expression consists of two what? Terms, yes. Each one of these is a term. So this is a term, and this is a term. So in algebra, this is one term and this is one term. And this term consists of two, what? What do we call? The term consists of two, B2 and C3, what do we call them?
Variables?
Well, you're speaking programming languages. No, now we're speaking math. So in math, this term consists of two factors, right? This term consists of two factors. So this is a factor. And this is a factor. So now the key idea to write a grammar that properly captures the precedence is to define the grammar such that on a high level, the expression consists of terms, and then we define a rule for a term. The term can have factors in it. So we divide it into two levels. The expression is defined in terms of terms. Then each term is defined in terms of factors. The term can have factors. So in other words, an expression can have an arbitrary number of terms, and the term can have an arbitrary number of factors. So this is the solution. So my expression now is going to be, now when we say an expression consists of an arbitrary number of terms, now these terms, what will they be? What will the operator be that connects the terms together? What operators connect terms together? Here, what's the operator? Plus. So it's either plus or minus. So an expression is either an expression plus term or an expression minus term, or both of these are recursive. So we need something that is not recursive. So what should I put here? Term. Now, on the lower level, I have a definition of term. A term can have an arbitrary number of factors. So what should I write now? A term, an expression can have an arbitrary number of terms with the operators being on this level plus or minus. Now at the term level, I can have an arbitrary number of factors with the operators being multiply or divide. So what should I write? A term is term multiplied by factor, or term, it's just the same thing but on a different level. So here, instead of saying expression, I say term, factor, by factor, or factor. Okay? Now what do I need to define now? I need to define a factor. And the factor is, what's a factor? Identifier or number. Okay? So now let's do the derivation for let's just change this C3 into, okay, A1 plus, let's say, 5 times B2. Let's do the derivation for this. So the derivation for this is, so we're doing the expression, forget about the assignment. And so for the expression, only this part, expression. For the expression, I have what? What should I substitute? Expression plus term, or expression minus term, or term? Expression plus term. So I have expression plus term. So this is the this is the expression, and this is the term. Okay. Now what's this term? This term is, it's term times factor. It's a term times factor. And what should I substitute for this expression? Does it have add? Yeah, so this expression, is it an expression plus expression, or expression plus term, or minus term, or just a term? It's just a term. Okay. And this term, of course, is a single factor. And this factor is an identifier. And this identifier is what? The A1. And what's this term? Term is a single factor. And this single factor is a number. And this number is 5. And this factor is, it's an identifier. And this identifier is B2. Okay. Any questions about this derivation? So now clearly this solves the precedence problem, because we already put the addition and the subtraction on a high level, and we put the multiplication and division on a lower level. Right? So we forced this to be on a lower level. And now we have the right derivation for this. So in this case, we multiply, then we add. Okay? So we first multiply. So imagine now a code generator. We don't do code generation in this course, but the code generator is going to process this tree in depth first order. And in depth first order, it's gonna do this multiplication before it does the addition. So just forget about depth first, but just think of it logically. Here we do the multiplication, then we do the addition. Questions? Okay. Now this is good and it's general, but it doesn't. There is one thing that it doesn't capture or generate, which is parentheses. What if we have something like this? A1. What if you have something like A1 plus B2 multiplied by 5 minus C3. Now this grammar clearly does not have parentheses in it. Now where do you think, in order to extend this grammar to account for parentheses, where do you think the parentheses will fit? Are they going to be on a high level or a low level?
Low.
Why low level?
Because you want to do that first before you do the rest of it.
Yeah, because they are higher precedence. In fact, higher precedence is lower level in the grammar and lower level in the derivation tree, because you want to do them first, right? So where do you think we should add them? Well, it's even lower, right? Think about this. So this is a term. This is a term. And this is another term. Now, within this term, how many factors do I have? I have 2 factors. Within this term, I have this factor, which is the number. And the other factor is the whole parenthesis structure. Everything within the parentheses. So everything within the parentheses is another factor, right? So it's just, I add it as another factor. But what should I put inside to make it general enough? Expression. So inside this, so the parenthesis structure is a factor, but within it I can have any expression. So this is an expression that you can have at this level. Okay? So now, to make sure that we understand how this works, let's write the derivation. Let's do the derivation for this. So, on a high level, so the derivation for the string only, not for the assignment. So we know that this is identifier equals, and this is the end of statement, but we are doing the derivation for only the expression. So this expression on a high level is what? Is it expression plus term, or expression minus term, or term?
Expression plus.
Minus 2.
No, on a high level, top level. What do I have? At the top level, do I see the minus or the plus?
Minus.
I see the minus. Because on the top level, I have this big term minus this term. So on a high level, I see this. So it's going to be expression minus term. Now I can do this term. This is easy. This term is easy. This term consists of how many factors? Just one factor. And this factor is an identifier. Don't skip any rule when you do the derivation. Make sure that don't go from term to identifier. Don't skip the factor, because term is a factor and the factor is identifier number or parentheses. So this identifier is what? C3. So this is C3. Now I have to do this expression. Now on a high level, what does this expression consist of? To substitute for an expression, this expression is a single term. And this term is term times factor. And now this term is what? This term here consists of how many factors? So this term is this. This is a single factor at this level. So this is a single factor. Now this factor is what? Yeah, this factor is parentheses, expression, parentheses, and then this expression is what? So you have to have a whole expression. So this is going to be expression plus term, and okay, so this is going to be, so I'm going to do it in this ugly way. So this expression is going to be an expression plus term. So this is, okay, expression. See if we don't have space, we're running out of space. I should have done this more compactly. But it's expression plus term. And then this expression is, so we're trying to derive this. So this is this. So it's an expression plus term, and the first expression is a term, and each term is a single factor. So this is factor, and this factor is an identifier, and this term is also a factor, which is an identifier. Okay, so I'm sorry that I don't have enough space here. In fact, yeah, and I don't even have enough room here. So this expression is expression plus term, and this term is factor identifier. Now, what's this identifier? This is A1. And what's this? A2, B2, sorry. And then what? What's left? This factor is number, and this number is 5. Now, is everything a terminal now? Do we have is every leaf a terminal? Every leaf is a terminal, right? So these are, terminals here in the context of compilers are tokens recognized by the scanner. So is everything in the leaves something that the scanner recognizes? So this is something that will get recognized by the scanner. This is something that will get recognized by the scanner. And this is an identifier, number, identifier. So everything is a terminal in our language, or in our context-free language. The terminals for our context-free language are the tokens recognized by the scanner. Now, does anyone have any question about this derivation with the parentheses? So does it make perfect sense? Okay, so now, so this is all the derivations that we did today were manual. So we did the derivation manually. And, in order to come up with a correct derivation, we had to look at this expression and to do some kind of matching in our heads between this expression and this grammar, right? So we did expression, then we made a choice to do expression minus term. So on this level, how many options did we have? We had 3 options: either expression plus term, or expression minus term, or term. And we chose this expression minus term. Now, how did we choose this? So this is a derivation that we did by inspection. And in fact, in order to choose this substitution, or this production, production number 2 to substitute for an expression, we had to look ahead. And we had to do some kind of understanding or digesting this expression and trying to match it with this. And then we figured that, okay, this would be the best substitution. But is this a systematic procedure that will always work? Like, is this an approach that you can use to parse a program that consists of 1,000,000 lines of code? Right? So how would you do it? It's like you have, at each level, you have multiple options, and you have to figure out what the best option is. So you need some kind of a systematic procedure to figure out the right derivation of a given string or a given program. Like I said, for us now, a program is just a string of symbols, no matter how large. So you need some kind of a systematic procedure to do the matching between this string and the grammar. And of course, also you need to determine if there is no matching, if the string is syntactically incorrect and it just cannot be derived using this grammar. So you need to determine if it's derivable or not. And if it's derivable, find the right derivation. If it's not derivable, then report an error. Report an error. Say, okay, you have a syntax error in your program, right? So this is what this is what parsing is. So parsing in a compiler is a systematic procedure for finding a valid derivation for a given program, or at this level, a given sequence of tokens. For us, at this level, the program looks as a sequence of tokens that were recognized by the scanner. This sequence of tokens, can we find a valid derivation for this or not? If there is a valid derivation, find that derivation. If there is no valid derivation, derive an error, report an error. And in this course, we will learn only one parsing technique. Because this is not a compiler course, but we'll just learn one parsing technique as an example. And this is what we will start working on next time.